with its entire. Okay, so let's kind of think of what's going on here. Okay, we know that the work done, if we have a vector field df that's moving a particle along some curve c, then we know that the work done is going to be equal to the integral along that curve of just f dotted kind of with that dr element. And we know we can rewrite this as integral c of f, let's see, f of rt dotted with r prime of t. Okay? But we also know from way back in the day, maybe not way back in the day, but we know that force equals mass times acceleration. That's Newton's second law. And so what this integral is going to kind of turn into is going to be integral along c of m times r double prime of t. I don't want that to look like the dot product. It's not the dot product. This is m times rt. These are the same thing. And now we're dotting with r prime of t dt. Okay? And so if we want to rewrite this just a little bit, I'm going to pull that m out. And being we have everything in terms of our parameters, I'm going to switch a to b. And so what this is going to be is r prime of t dotted with r double prime of t, or r prime r double prime of t dotted with r prime. And we actually proved a theorem way back in chapter 2. This thing, we proved that d dt of r prime of t dotted with itself equals 2 r prime of t dotted with r double prime. And so we can rewrite this integral one more time to be m over 2 because of that 2 right there. So that's going to kind of turn into here. And this would just be d dt of r prime of t, not r prime. Okay? And now we have m over 2 times the integral of a to b of d dt. And whenever we have the dot product of something with itself, that's just the magnitude. But we also have the derivative of the integral. So by the fundamental theorem, this is just going to be m over 2 times the magnitude of rt evaluated from 0 up, I'm sorry, this is 50 squared. Magnitude squared up evaluated from A up to B. Which looks like 1/2 m r prime of B squared minus 1/2 m r prime of A squared. Okay? And remember, being that r prime is just the velocity vector, we can rewrite this one more time. 1/2 m times the magnitude of the velocity squared okay? Now, if you've taken any physics class, then you might recognize the fact that we kind of name kinetic energy as 1/2 mv squared. And so this equation here can be written one more time as just the kinetic energy at B minus the kinetic energy. So in other words, that line integral is just the change in kinetic energy. Okay? So I'm going to kind of let that sit for just 1 second. We're going to kind of pretend this is just equal to that integral. Okay? But now what I want to very briefly do is, we know that f of x, our big f of x, y, z, equals the gradient of some function, some other function, f of x, y, z. And I want to kind of declare one more function that's just going to be the negative of that little f. And we're going to call this negative p, lambda p. And we're going to call this the potential function. And so that's from physics. It's actually defined as being the negative of the negative of the gradient, or the function from where the gradient comes. Okay? And so then the integral of f dr is going to be negative integral dp, or the gradient of p dr. But we know, because this is the gradient, we can apply the fundamental theorem of line integrals one more time. And we're going to have negative p of b minus p of a, which is going to equal p of a minus p of b. So in other words, kind of what this is going to look like is that we know that the loss in kinetics, the gain in kinetic energy is equal to this line integral. And it's also equal to the loss in potential energy. And we can just use that very briefly to prove, if we add k of a to the other side and add p of b to the other side, we would get k of a plus p of a equals k of b plus p of b, which is just energy conservation. Okay? So in other words, the sum of kinetic and potential energy at the beginning sum of the kinetic and potential energy at the beginning is the same at the end. No energy is lost. Okay, so we just use calculus to prove, the law of the conservation of energy. We use the fundamental theorem of line integrals. Okay, so that's going to do it. That's the whole video. I hope that this has been helpful. If you have any questions, we can talk about it in class tomorrow. So, great.